Today we try to prove a geometry fact with complex number as part of the mastering complex number series. So you know that Ptolemy inequality here saying that for a convex quadrilateral A, B, C, D here, we would have this inequality AB, the opposing sides, times CD, the length of the segments, plus BC times AD here, right? So the sum is greater or equal to the product of diagonal AC and BD. Now you know that inequality happens if A, B, C, D are on the same circle. Now how do we prove that? There's geometric proof for the equality case by using similar triangle. There is trigonometry proof with sine and cosine. But here we'll use complex numbers. Let's recall that for two complex numbers, z and w here, the difference would be, you can imagine in the complex plane, just make the connection with the endpoints. So the difference here from z to w would be representing the difference w minus z. All right, that's important. It is actually very useful to understand the geometric meaning of the addition, difference, multiplication, and division of complex numbers. Here we're going to use difference and addition here, right? So if we're going to place this A, B, C, D in a complex plane, we would have lowercase a, b, c, d representing the complex number corresponding to the vertices a, b, c, d, right? So with that, we know that the ninth segment AB, the length, would be the modulus of the difference of a minus b, the lowercase a minus b. That is, we have this relation here, okay? So again, the meaning here is this bar means the modulus of complex number. Remember that a, b, c, d lowercase representing complex numbers. So a minus b, it is actually here, right? So the modulus would be the length in the geometry, the AB segment, right? The length of AB segment. Now similarly, for a BD, you would be B minus D, right? I didn't mark it out here. So what that means is, in order to prove the inequality earlier, right? So we have this relation between the ninth segment and the difference of complex number and the modulus of the difference. So the inequality here, we can rewrite it as, we need to prove some inequality for this complex number a, b, c, d, lowercase, right? So a property of the modulus is that the product of the modulus equals the modulus of the product. So we're going to rewrite that. All right? So these are equivalent. So this is something we want to prove now. From geometry, we turn the problem into a complex number algebra problem. All right? For this inequality here. Of course, for easier notation, we're going to call this complex number z and w. Okay? So let's do that. So that's z here, right, and w. So now this inequality becomes, I'm going to prove the modulo of z plus the modulo of w is going to be greater or equal to that. All right. So of course, immediately you may think, oh, there is what is called triangle inequality for complex numbers, right? Indeed, for triangle inequality here, we have that z and w are going to be greater than z plus w. Of course, this is a wrong diagram, sorry. This is a difference, okay? But the idea is the same. For the addition, you're going to have another diagonal here. But it is always true that for the complex number z and w, you would have this inequality here. Now, when does the equality holds? Equality holds when z and w, the angle, are the same, all right? So here, z is modulus, right? So equality holds if now the notation here is the actually argument, this is called argument of the complex number, equal to each other, okay? That's when the equality holds, all right? Let's go back to our original problem, right? So we try to prove z, w greater or equal to this modulus here, right? Where z is this by definition, right? Z and W. What we're gonna do is we're gonna expand out z and w here, right? This using the typical operation of complex numbers, right? So we have z, when you expand it out, it's gonna be AC minus AD minus BC plus BD. Now similarly for the W, right? You're gonna expand it out, we're gonna get this. Now notice, however, when you add them up, we're gonna have terms cancel. Okay, so AC gonna cancel with CA here, right? And another term here is BD will cancel with BD here. So when you add it up, these two pairs cancels. So we're gonna have another 4 terms here, and these 4 terms happens to be the right hand side of this inequality here. All right. So which means we have the proof by using the complex number triangle inequality. All right. So z plus w on the left hand side happens to be the quantity here on the right hand side. Okay, that's the proof using the complex number inequality. All right, so that's let's review what we get here is from the geometry, and we turn into complex number problem, and we use complex number inequality to prove that. Now we're gonna ask, when does equality holds? Remember, equality holds when z and w have the same argument, right? The angle are equal to each other. Now, of course, you know that what is z and w, right? So z is a product of 2 complex numbers, and the argument of multiplication of complex number is addition of the argument. Okay, so in other words, what we have here is from this, the condition for equality is that the argument is equal to each other. If we shift around, the difference of argument would equal the difference of argument here, right? And this, you can think about it offline. What this word tells us is that the angle BAD would equal 180 degrees minus the angle BCD. In other words, they should add up to 180 degrees, which is a condition for them to be concyclic. They have to be on the circle in order for the equality to hold. So today we used an interesting approach in proving this geometric fact. Now we do have other interesting problems relating to complex numbers. Do check out the Mastering Complex Number series. In the meantime, please like, share, and subscribe to the channel.